Okay, let's look at this example. Primal is the problem that we have actually solved before using the simplex method. And the dual of it is the first column here, 1 minus 1 becomes the first row in the dual, so on and so forth. The second column becomes the second constraint of the dual. And W1 is associated with this, W2 is associated with the second constraint, X1, X2, they are associated with the first and second dual constraints, respectively. Okay, so in this case, for the weak duality theorem, I need a pair of feasible solutions. For example, I don't know which solution I picked. I have picked x equals 0 and 4. This is supposed to be a feasible solution to the primal. And for w, I picked 3, 0. This should be feasible for the dual. Let's just check. 0, 4, yes, the first constraint is satisfied. The second constraint, 2 times 4 is 8. Yeah, it is feasible. For the dual, 3 greater than 1 and 3 greater than or equal to 3. And everything is non-negative. So this is feasible pair of solutions. They're both feasible. And if you look at Cx, how much is it? 0 plus 3 times, so that's 12 for the primal problem. And for the dual problem, WB, the objective value induced by 3, 0 is 6 times 3 is 18. And what am I supposed to have? I'm supposed to have the maximization value bounded above by the minimization value, right? This is what we're supposed to have. Do we have that? Yes. This side is 12, this side is 18, so one is a bound on the other one. The inequality is for sure satisfied. So that demonstrates the strong weak duality theorem. For the strong duality theorem, I know from before that the optimum solution was, what was it? 3/14 or something like that. What was it? 4/3. 4/3 and 14/3. That was the optimum solution for the primal problem, which you can find either graphically or using the simplex method. And to find the dual solution, you can use the complementary slackness conditions, or I can simply propose a dual optimum solution to you, and you can see that they satisfy the strong duality theorem. So it turns out that the optimum solution for the dual happens to be 5/3 and 2/3. This is the optimum dual solution. Optimal to P, optimal to D. Obviously, if you've got the information that x bar is optimal to P, it implies that some optimal solution must necessarily exist for the dual. What it is, I don't know, but it exists, that's for sure. Okay? And so, how you find it is another matter. First, you must make sure that things exist before you actually construct them or find them. Number 2, Cx bar must be equal to W bar B. Are they? 4/3 times, well, 4/3 plus 3 times, that's 46/3. This part is 46/3. How much is the other one? 6 times, so that's 30/3, 16/3. That's 46/3 again. Yeah, they are equal. Complementary slackness conditions, or the complementary slackness theorem. What are the complementary slackness conditions? Well, I have 1, 2, 3, 4 conditions, okay? One for each pair of variable and constraint. The first condition is W1 times x1 plus x2 minus 6 is equal to 0. Then W2 minus x1 plus 2x2 minus 8, that's supposed to be equal to 0. The next condition is x1, W1 minus W2 minus 1 equals 0. x2 times W1 plus 2W2 minus 3 is equal to 0. Okay, so these are the conditions. And if you had, for example, the point 4/3, so this is how you apply application of the conditions. If x bar is proposed to be, say, 4/3, 14/3, then from here I can simply apply the complementary slackness conditions to find actually the optimal dual solution, because it will produce sufficient information in this case. So W1 times, well, first of all, 4/3 plus 14/3, that's 18/3 minus 6. So the first one gives you nothing about W. The second one, W2, how much is this? Minus 4/3 plus 28/3. Is that 0?
Minus 8 is 0.
Yeah, that's 0 also. So nothing again. X1 is 4/3. So the quantity in parentheses must hold as equality if you require 0 here, which means you have an equation here. W1 minus W2 must hold, that particular constraint must hold as an equation or as active. Similarly, X2 is 14/3, which means W1 plus 2W2 minus 3 must hold as equation. So if you solve these, W1 minus, so that gives you 0 minus 3W2 equals minus 4. What is wrong here? Minus 2. This part?
No, right hand. 4. It's right hand side. Minus 3 W2 is equal to minus 2.
Oh, okay. Why? I'm multiplying this by minus 1.
1 plus 1.
You add them. That goes. That minus 2. That's minus 3.
Okay, the right hand side is minus 2.
Oh, I see. All right. This part is, there's nothing wrong with that. That's minus 2, okay. W2 is 2/3, which implies W1 is how much? 5/3. Okay? All right. Let me just point out one pitfall here. So, take this time x to be, for example, 0, 4. This is your x bar. If you use the complementary slackness conditions, W1, x1 plus x2 minus 6, how much is this? That's going to be W1 times 0 plus 4, so that's going to be minus 2, right? Which implies W1 is equal to 0. So I already concluded that W1 is equal to 0. W2 times minus x1 plus 2x2 minus 8, that's going to be 0. So that's simply W2 times 0. So there's no information here, no info. And x1 is 0, so 0 times whatever you have equals 0. It doesn't produce any information. But x2 is 4. 4 times the second constraint, W1 plus 2W2 equals 0, gives you W1 plus 2W2 equals 3. But W1 is 0, which means W2 equals 3 over 2. So now you have a solution which satisfies complementary slackness conditions. Let's look at the Cx value. How much is it? Let's make these bars. How much is Cx bar? 12. How much is W bar B? 0 and 3 over 2. Where is it? 6 times 8. Okay. 6 times 0 plus 8 times, right? 8 times 3 over 2. How much is that? 12. So the objective values are also equal. So why this is something that need to be cautious about? The objective values are equal. The complementary slackness conditions are satisfied. So everything seems to fit. These are supposed to be optimal solutions, one is tempted to conclude. But that's incorrect. What is wrong here? Infeasible. W is not feasible. See, I told you. You have to be particularly careful about feasibility. Otherwise, you will get the incorrect conclusion. I know that I tell this maybe sometimes 3 or 4 times. Still, there's someone who gets the wrong conclusion. I don't know. That's maybe in the exam, sometimes you are so, concentrated on what you're trying to do, you forget all this. See? Don't. Of course, when you have infeasibility, the theorem does not apply any longer. Okay? There's also the thing called homogeneous dual. Let's take a minimization type primal problem, say in canonical form. Okay. Now the regular dual for this is, what is it? Maximize WB subject to WA less than or equal to C with W non-negative. That's your normal dual. We had corollaries which said that if one problem is unbounded, the other one is infeasible. But the reverse implication was not quite right. Okay? If one is infeasible, the other one is either unbounded or infeasible. Now, to avoid that complication, well, it's not a complication, but rather than having either or type of statement, we want to have if and only if type of statement. For that reason, the so-called homogeneous dual works quite fine. So let me write down the homogeneous dual here. The homogeneous dual is essentially the same as the dual, except that the right side here is replaced by the 0 vector. Okay? So this is the homogeneous dual. When you replace the right-hand side elements by 0, what are you actually looking at? You're looking at directions, right? The directions of the feasible set. Okay? So that's what you're looking at here. Okay? Now, what is the primal problem corresponding to the homogeneous dual? So this is the dual of the homogeneous dual. Dual of the homogeneous dual, what is it? 0 times, so it's maximization, 0 times what? X subject to A, X less than or equal to, this is minimization, sorry, minimization, less than or equal to B, X greater than or equal to 0. So, of course, this is similar to this, except that the objective function is different. Okay? So, here's a question.
X greater.
Yes. That maximization confused my pattern of thinking. Okay, so here there's a theorem which says the following. P is infeasible if and only if the homogeneous dual corresponding to it is unbounded. So assume P is infeasible. We must show that homogeneous dual is unbounded. Anybody? Can you show that the homogeneous dual is unbounded? Well, let's begin with this. If P is infeasible, then what do we know about the regular dual? Regular dual is either infeasible or unbounded. Now, is it possible for D to be infeasible? Or how do I go from there to here? That's the question. Yes?
Homogeneous dual unbounded o zaman primal homogeneous primal infeasible olacak.
Okay, let's look at this one. Well, I don't know. That probably does not produce any information. Let's look at the homogeneous dual. If the homogeneous dual, how do we put this? Let me just say. Okay, this is the way we should look at it. If you look at P and DHT, the feasible sets are the same, okay? So I'm not sure if this is any useful information. Let's just erase that. If P is infeasible, then DHT is also infeasible. Because their feasible sets are the same, the constraints are the same. So the fact that DHT is infeasible implies that HD is either infeasible or unbounded. Okay? Now, can HD be infeasible? Yes or no? It can't be. Yes. W equals 0 is a feasible solution to HD, hence HD must be unbounded. That's the only possibility left. Okay, so that's the first part of the proof. The second part, assume HD is unbounded. Then what does that say about P? Well, first of all, DHT is infeasible, which means P is also infeasible. Because DHT and P have the same feasible sets. If one is infeasible, the other one is also infeasible. Okay, so that's what your homogeneous dual does. Economical interpretation of the dual problem and the so-called shadow prices. This is again a special term, and you will hear that here and there, so you need to know what they are. So I'm going to consider a problem of this sort. Canonical form maximization problem. X is a vector with n components, and xj, we're going to interpret xj to be the number of units of product j to produce. So you are a firm that produces n different products. Cj is the profit level per unit of product j. So that CX stands for the maximization of the total profit. But then you have different resources. So we have constraints. And each constraint stands for a resource. So we have m different resources, and BI is the available amount of resource I. Okay? It's an upper bound on how much you can spend of the ith resource. And the ith constraint tells you that whatever you use as resources should not exceed the available amount. So let's interpret Aij to be the number of units of resource I consumed by 1 unit of product j. Okay. So if you look at the ith constraint, it simply tells you AI1, X1, up to AIN, XN, less than or equal to BI. Now, the first term here, AI1, is the ith resource consumption, or the number of units of resource I consumed by 1 unit of product j. If you have x1 units of product 1, then of course that's the total you use up of resource I for producing x1 units of product 1. So on and so forth. The last one is the consumption of resource I due to producing xn units of product n. So left side is the total amount of resource I used by the production amounts x1 through xn. Okay? So what is the jth column, by the way? A1, J, AM, J. This is the column associated with the jth product, xj. What does it tell you? Product j consumes A1j units of the first resource, A2j units of the second resource, so on and so forth, etc. So this is the consumption vector associated with product j. Okay. Now when you look at the dual constraints, the jth column here for the A matrix tells you what the jth dual constraint is. What is the jth dual constraint? W1, A1j, W2, A2j, etc. WM, AMJ. That's the left side of the jth dual constraint. You see, this is a column vector, and the dual variables go with, and with the rows of the A matrix. So, in particular, you've got this relationship here, and that's going to be what? Great Dual problem will be a minimization, so this will be a greater than or equal to Cj. Okay? J going from 1 to n. Okay? And xj is your dual variable here, primal variable. All right. The dimension of Cj is, that's profit per unit of product, so that's going to be Turkish liras per unit of product J. We're looking at just the jth constraint here. And the dimension of the right side is monetary units, dollars or Turkish liras per unit of product J. On the left side, Aij is what? This is a summation. So if you look at the ith term of the summation, it will have Aij. What is Aij? Units of resource I. So units of resource I per unit of product J. That's the ith term in the summation. As a multiplier, you've got W1 for that. Of course, whatever dimensions you've got on the right, you should have the same dimensions on the left. So the dimension here should agree with the right side, which means that this is supposed to be Turkish liras, right? And then unit of resource, per unit of resource I. So that units of resource I cancel out. What you have is Turkish liras per unit of product J. Left side and right sides agree. This is the so-called dimensional check. Okay? All right. So this is what you have for Wi, the ith variable. So Wi simply stands for a monetary amount or monetary value assigned to the ith resource. And it's called the shadow price for resource I in this particular setting. In a different setting, of course, it may require a different interpretation. So let's assume now that we have an optimal basic feasible solution defined by a basis B. In this case, of course, X optimal is defined by B inverse B and 0, like that. The optimal objective value Z bar is going to be CB B inverse B. That's how much you have. But then if you define this, so let's define W bar to be CB B inverse. That's what I did in the proof of the strong duality theorem. Okay? So if you define W bar in this way, this part will be W, so that's going to be W bar B. And if you write this as a summation, it's simply Wi bar Bi. I going from, say, 1 to m. So you expressed Z bar as a summation of this kind. Now, if you ask yourself, what if I change the availability of resource I by 1 unit? Make it go up, for example. Then it tells you that your objective function, let me make this z rather than z bar. Your objective function the partial derivative will be equal to wi bar. Okay? Which means that if you increase bi from its current value to 1 more unit, bi plus 1, you're changing your objective value by wi. Since we're trying to maximize, if wi bar is positive, it's good to actually make that change in the availability of the ith resource because you get something. Okay? If this is 0, you get nothing by increasing your ith resource. If it is negative, you increase the resource, but you go down. Well, I suggest that you don't do that, okay, if you're maximizing. All right, so at least this tells you what the situation is. All right, let's just continue a little bit further. Does that make sense? Okay, so it does make sense. Let's just also observe the following. If I define W by CB B inverse, this is equivalent to W bar times B is equal to CB. You're post-multiplying both sides by B, okay? All right, so that set of equations is the same as this set of equations. Which means that the values you assign to the resources, the coordinates of W bar, are affected only by the basic costs and the basic columns, nothing else, okay? So, the shadow prices are defined only by basic costs and by the basic consumption vectors, the ones that go into the basis matrix. And so the non-basic ones have nothing to do with the situation, okay? B is not an optimal basis, then what do we know? Then Rj for some j is negative. Reduced cost will be negative. Right? Barring degeneracy. Okay? So Rj will be there will be, well, actually it has nothing to do with degeneracy. If B is not optimal, then you must have at least one non-basic variable that qualifies to enter to improve. Whether or not you can actually enter it is a different matter, but it qualifies to be entered. Okay? All right. What is Rj? W or CBB inverse AJ minus CJ. Okay? And if you take this as your W for that particular basis, This simply says that W times AJ is less than CJ. So the values assigned to the resources by that particular basis, they are not good enough because they actually, in your dual problem, you're trying to make these greater than or equal, okay? But you haven't been able to accomplish that. So it simply says that whenever this is the situation, your shadow prices don't really pay off enough, okay? So do enter this, improve your basis or improve your combination of productions so that it actually turns the other way around. So it also tells you the shadow prices assigned by any basis to the resources. You always want the final combination where W times each AJ greater than or equal CJ, okay? And whenever that doesn't happen, you're not optimal yet. Any questions on the economical interpretation? Well, of course, this can be taken further, which I'm not going to do, but every kind of linear program can have its own interpretation, and it's an interesting subject in my judgment. Nevertheless, we will leave that to the economists rather than to industrial engineers. Okay? Any questions? Okay. We'll see you at the exam time tomorrow. Good luck.